Let's begin with a differential equation, a system of equations. It can be expressed as y prime equals py, where p is a n by n matrix, y is a y and y prime are vectors with n components, each component being a function of a single variable t. This equation is defined on a t interval from a to b. The p matrix is continuous on the interval from a to b. As we've seen, this ensures that there is a solution for any initial condition we might specify. That is, for any t naught between a and b and any vector y naught, there is a solution such that y of t naught equals y naught. Now let's let y1 through yn be a fundamental set of solutions, so that psi of t, the matrix consisting of the columns y1, y2 through yn, is a fundamental matrix. The general solution to the equation is y of t, and it can be written as psi times a c vector, and the general form of the solution, as we know, would then be a linear combination of the y1 through yn, c1 y1 plus c2 y2 up through cn yn. Now c is the column vector c1 through cn, and we implicitly assume that we know that. Excuse me, that we know that at this point. Okay, now we write out the condition that I mentioned up here. For any t naught in the a, b, and any vector y naught, of course, vector y naught of the same dimension as the solution vectors, there's a solution with y of t naught equal y naught. That is, for any given initial condition, which is what this is, there's a solution to the equation because p is continuous on the interval of definition. Well, since there's a solution, the solution has to be of the form of a solution. Remember that the general solution is just this, so that the solution must be of this form for appropriate values of c1 through cn. Now the condition on this solution would be that if we plug t naught in, we do get the vector y naught. So that since this vector that has to be equal to y naught when t equals t naught is of the form psi c for a c of this form, psi of t naught times c is going to have to equal y naught, because of course psi of t naught times c is just this evaluated for t equals t naught. This can work if and only if this psi matrix of t naught is invertible. Since it's invertible, its determinant has to be non-zero, but what's the determinant of psi of t naught? It's just the Wronskian of t naught by the definition of the Wronskian, so we conclude that the Wronskian is non-zero. Now, there was no assumption of what value between a and b corresponds to t naught. T naught could have been any value between a and b, and this still holds, meaning the Wronskian is non-zero for every value of t naught between a and b, so that the Wronskian is non-zero on the whole interval from a to b at every point between a and b. And we've proved the following, which is a theorem, so we'll go ahead and glorify this by calling it a theorem. If y1 through yn is a fundamental set, it follows that the Wronskian of t naught is not zero for any t naught in a, b, where the Wronskian naturally is the Wronskian that corresponds to this fundamental set. That is, the determinant of the psi matrix whose columns are the members of that fundamental set. Now we can combine this with the result that we saw recently. In order to be a fundamental set, there must be some point t naught in AB where the Wronskian is non-zero. So if the Wronskian is non-zero at some point t0, then it has to be non-zero at every point t0. Because if the Wronskian is non-zero at one point t0, this is a fundamental set, and it has the property that the Wronskian's non-zero at every point of the interval. We conclude that this is a fundamental set if and only if the Wronskian is never zero on the interval AB. So we have two equivalent conditions. Wronskian's never zero in AB, and this is a fundamental set. These fundamental sets and fundamental matrices have one more important property. If this is a fundamental set, y1 through yn is a fundamental set, and y1 hat through yn hat is any solution set, then first of all, there's a psi matrix that goes with this, and there's a psi matrix that goes with this. We'll call this the psi matrix here, the psi of t matrix, and we'll call this the psi hat of t matrix, the matrix that goes with this solution set. Now remember that a psi of t isn't necessarily a fundamental set, it's just a solution set. So there's no assumption that this is a fundamental set, that every solution of the differential equation will be some linear combination of these vectors, these y hat vectors. We do assume that for the y1 through yn vectors. In any case then, given a fundamental set of y's and a solution set of y hats, if we form the psi and psi hat matrix, they are connected in the sense that if we take our fundamental matrix and multiply it by some matrix C, we're going to get the psi hat. That is, there exists a matrix C such that it can be multiplied on the right, such that the psi matrix can be multiplied on the right by the C matrix to give us the psi hat matrix. And I can even put a stronger word in here. This matrix C is unique. There's just one such matrix. So for any solution set, there is one and only one matrix that connects these solution matrices, that connects the solution matrix to the fundamental matrix. Furthermore, it works both ways. If C is invertible, then the psi matrix would be the product of the psi hat matrix by the inverse matrix. And in that case, since psi is a fundamental matrix, psi hat would have to be a fundamental matrix. So that psi hat is a fundamental matrix if and only if C is invertible. This means that if the matrix C that connects the psi matrix and the psi hat matrix in this manner is invertible, then psi hat is a fundamental matrix, and this is a fundamental set. And if C is not invertible, then this isn't a fundamental matrix, and this is not a fundamental set. If this is not a fundamental set, then there are solutions that can't be formed by combining these solutions. Just to see what this sort of thing can look like, let's go back to the first system of equations, the very first system of equations we solved, where we got the psi matrix, e to the t, negative 2 e to the t, e to the 7t, e to the 7t. Let's let C be any matrix A, B, C, D. If we multiply psi on the right by C, this is what we get. And this will be a solution matrix. In any case, this is a solution matrix, which means that this vector and this vector, written here as vectors inside braces, are solutions, so that this is a solution set. If C happens to be invertible, then that, of course, means that the determinant of C is not 0, so AD minus BC is non-zero. Then, if we choose the A, B, C, and D such that this condition holds, this is, in fact, a fundamental set.